Okay, so we are now going to talk about physical pendulums. So, thinking back to simple pendulum. So a simple pendulum was where we had some little mass m attached to some massless string that was oscillating back and forth. Now, physical pendulum, that's where the whole object has mass. So like the string or whatever is oscillating has mass. So what I think about for a physical pendulum, like something like a grandfather clock, that whole thing has mass, it's oscillating back and forth. It could be like a punching bag oscillating back and forth. It could be the legs of a human or animal oscillating back and forth. It could be a green sheet of paper just oscillating back and forth. Lots of things. So let's go ahead. I'm going to go ahead and just draw a blob, which is going to be my physical pendulum. Great. Okay, cool. So that's my physical pendulum. So this X, I'm going to go ahead and draw that. So that is my point of rotation. Great. So a couple of things I want to label on my physical pendulum. So it'll come in handy. We're going to need to know our center of mass. So this right here is going to be, I guess center of mass is going to be closer to the more massive end. So this is the center of mass of this object. And then we'll say this object has some mass. Cool. So our equation for the period of a physical pendulum is T, and I'm going to call PP for physical pendulum, is going to be 2 pi root I over mgd. So let's go ahead and define a couple things. So period, we know what that is. That's the period. So that's the time for one complete revolution or one cycle. And we'll oftentimes measure that in seconds, but we could use different units. I is moment of inertia. And we'll oftentimes use kilogram meter squared for those units, but again, other things are acceptable too. M is the mass of the object. And again, we'll oftentimes use kilograms, but other things are acceptable as well. G is the acceleration due to gravity wherever the object is. So oftentimes on Earth, that'll be 10, but we could go to a different planet and mix it up. D, and I will go ahead and draw that on my picture as well. But D is the distance from rotation point to the center of mass. And let's go ahead and draw that on the picture too. So this is D. So always, it's very easy to make a silly mistake and not use the correct D, but always the distance from the center of mass to point of rotation. So always, when you have a problem involving a physical pendulum, I would always label the center of mass, label the point of rotation, and then you can label D after that. Great. So let's now go ahead and solve a problem using the physical pendulum equation. Cool. So I would encourage you, read this problem. You can solve it yourself. Pause my video, and then you can come back and watch it together and check your answer. Cool. So I'm going to go ahead and read it. So we have a leg of mass m. Cool. So I'll go ahead and draw that. That's the good old leg. And let's go ahead and assume, leg is like a uniform rod. So this is my pivot point. So this is, I should draw that. That's my pivot. This is the mass of my leg. So it's what? Mass m. And then this is length L. Great. So again, first thing that I always do when I solve these problems is I go ahead and label the center of mass. So this is a uniform rod. Makes our life easier. So the center of mass is going to be right in the middle. So that is going to be center of mass. And again, D, which we talked about in our equation, is your distance from the center of mass to your pivot point. So I will go ahead and label that on my picture. Cool. So first thing, and I should have done this at the beginning, excuse me. I'm going to write down my equation for period of a physical pendulum. So that's 2 pi root I over mgd. Cool. So now let's see what we can plug in. So I, moment of inertia. Okay, so this is a rod rotated about the end. So is that 1/3 ml squared or 1/12 ml squared? So looking at my moment of inertia of shapes, it looks like that is 1/3 ml squared. And just as a reminder, 1/12 ml squared is if the rod is rotated about the center. But in this case, legs rotate about our hips, so that's the end. M is just the mass of the object, so that's just going to be M. G, that's just acceleration due to gravity on Earth, so that's just G. And D, we said that's the distance from the pivot point to the center of mass, which in this case, D is just going to be L over 2. Cool. Let's write that down. So D is L over 2. So let's go ahead and plug that all in. So we have 2 pi root what? 1/3 ml squared over m. G and D is L over 2. Cool. So it looks like we're going to have some fun simplifying. So it's going to be 2 pi. Wow, that's nice. M's cancel. 1 L cancels. That 2 is going to go to the top, so it's going to be 2/3 L over G. Great. So we have our answer. Okay, so now let's go ahead and try part B. So if you increase the leg length of a person, what will happen to the period of motion? Okay, so if I increase L, then our period, yeah, that's going to increase as well. Those are directly proportional. Cool. So I like to think about that just in general. So like if you think animals with longer legs, so animals with longer legs, so that's like a giraffe, an elephant, all those things. Those have a pretty big period. I like to think of it as like some of my friends that are pretty taller. Like one of my friends, Mr. Hollenbach, he has very long legs. When I see him walk across the school, it looks like he has a very slow, like very chill, relaxed period. So that's going to be Hollenbach as my real life person. I'm sure you all have your own person as well. Now I like to think about it too. Animals with shorter legs. So, okay. So, if I can spell that word, animals. Animals with shorter legs. So if I decrease L, so now I'm going to go ahead and let's say L is decreasing. Yeah, the period will decrease as well. So period decreases. So they have to walk a lot faster. They have a much faster walking pace, animals with shorter animals with shorter legs. So like if I think about that, like mice, yeah, little dogs, like they have to really scamper to keep up. I have like one friend named Mr. Hawkshield whose legs are a little bit shorter, and he really has to walk a lot faster than his friend Hollenbach, or I should say, his legs have to turn faster, so he has a shorter period. Wow, that's so cool to see it. But I encourage you to think of whatever friends you have who that might relate to. Cool.